Okay, this is the investigation for logarithms. I call it the Wizard of Log. I actually have another version of this investigation based on the movie Matrix, but I have found that over the years that I have taught IB Math, that movie has gotten older and older, and although I think it's a classic, I guess the younger generation doesn't, and fewer high school students have actually seen The Matrix, although most of you have seen The Wizard of Oz. So I have pretty much resorted to only giving the investigation for Wizard of Log, but we can discuss Matrix if you have seen Matrix. I think Matrix is a classic science fiction movie, and it has a good analogy to logarithms also, just like Wizard of Log does, okay? All right, well, let's go to the second page. Okay, so let's take a look at the Wizard of Log. In the Wizard of Log, Dorothy lives in the regular old world. It turns out that the state in America where she lives, Kansas, is actually my home state also. It's not black and white there, but in the movie it is, okay? And let me go ahead and write some notes here. You can write these same notes in your note sheet. In this investigation, it's actually important for you to have different colored pens or pencils to take your notes in, because that's one of the ways we differentiate the different kinds of numbers, okay? I suggest black, blue, and red for the colors. Okay, so what I'm going to do is I'm going to use black to signify things that have to do with the regular old world. In this case, it's Kansas. And then I will use red for in the exponent world, which we also called the world of log. So I'm going to name each world first of all. So the regular world in the Wizard of Oz is called Kansas, and the color scheme is black and white. And the people are regular size people. And you're like, what do you mean by regular size people? I mean, just like us. Okay, so, and then I'm going to change to the red pen to talk about the things related to the land of log. In the land of log, there are many colors, as you saw and were reminded of in the summary video. The people size, well, I'm talking about the native people of the land of log, who are the munchkins. They are small or munchkin sized. Okay, and let's go back to the PowerPoint. So in the regular old world, everything's in black and white, including the numbers. The numbers we're going to write in black and white. And the numbers are very familiar to us. They've been with us our whole lives. We know them well. We know how they work. We know all the math rules that apply to these black and white numbers. There's no place like home. There's no place like home. So remember, the black and white numbers are the numbers that you know and love today. In the land of log, where everything is colorful and magic and munchkin-sized, we have different strange numbers. I'm going to make these strange magical numbers. I'm going to use red to color these numbers in, okay? So, for example, they look exactly like our numbers, except they are colorful and they are small, just like the people in the land of log. And the people in land of log are small and colorful, right? And the numbers in the land of log are also small and colorful. The black and white numbers in the regular world, we're going to write in black. Okay? So who is in the old world and who is in the land of Log? Well, Dorothy is both in Kansas and in the land of Log, except in Kansas she's black and white Dorothy, and in the land of Log she is color Dorothy. Just like some numbers which exist both in Kansas and the land of Log, such as 10,000 and 10 and 1 and 0.01. All these numbers exist in Kansas, and they also exist in the land of Log, except for 10,000 in the land of Log is a red 4. And 10 in the regular old world is the red number 1. These are small also. I just didn't make them small here because it'd be hard to see. And 1 in the regular old world, Kansas, is red 0 in the land of Log. And 0.01 in Kansas is negative 2 in the land of Log. So just like Dorothy is black and white in Kansas and colorful in the land of Log, but it's the same person, 10,000, 10, 1, and 0.01 in black and white in the old world are actually 4, 1, 0, negative 2 in red numbers in the land of Log. 10,000 is red 4. 10 is red 1. Okay? We're going to talk more about that in a second. Let's talk about some of the characters in Kansas who don't exist in the land of Log. For example, Uncle Henry and Auntie Em. Those are the relatives that take care of Dorothy in Kansas. They are like negative numbers, because negative numbers that we know and love in Kansas in the old world do not exist in the land of Log. Actually, the red negative 2 isn't even a negative number in the old world. In the old world, it's actually equal to 0.01. So negative black and white numbers don't even exist in the land of Log as themselves. Okay, just like Uncle Henry and Auntie Em, they don't exist in the land of Log when Dorothy goes there. Okay, so let's see if there's anything to write in our notes here. So, characters who exist in both worlds, and how do they look different in each? So, Dorothy exists in both worlds. So there's Dorothy, black and white Dorothy, and then there is color Dorothy. Okay? And, of course, there's the dog, too. The dog is named Toto, by the way. And characters who exist in the real world only, the Uncle Henry and Auntie Em characters, only exist in the regular world. They don't exist in the land of Log. Examples of magic. Let's go back to the PowerPoint, shall we? Okay, so let's talk about magic. There is magic in the land of Log, which is the exponent world. In the regular old world, we just have the regular math operations that we've always lived with. Okay, so for example, we have addition, subtraction, multiplication, and division. And multiplication and division are kind of like the challenging math operations that we learned later in school, and especially division is quite difficult, right? So multiplication and division are time-consuming processes in our regular old world in Kansas. It turns out that if we go to the land of Log, we can do magic and do the same operations. Okay, let's go back for a second. 10,000, black 10,000. Why is it equal to red 4? Okay, basically all the numbers in the land of Log are equivalent to how many zeros there are in the black number. So there are 4 zeros in black 10,000. That is why it is red 4. There is 1 0 in black 10. That is why it is equivalent to red 1. there is 0 zeros in black 1. That is why it is equivalent to red 0. Okay, then we start getting weird here with 0.01. But before we go there, let's talk about why black 10,000 is red 4. Basically, the way you figure out what the red equivalent is of the black number is you try to express the black number 10,000 in the form of 10 to the something. 10,000, black 10,000, is equivalent to 10 to the 4. And that is why we say that the red 4 is an exponent. And remember, exponents are like little numbers that you put in the corner of a base to the exponent. So that is why the red numbers are considered small, because they're exponent numbers. Okay? Now that we know that red 4 is equivalent to 10 to the 4th in the old world, now we can look at the red -2, which is 10 to the -2 in the old world, which is 0.01. Okay? So do you see how the red numbers that are negative actually correspond to small numbers in Kansas? Okay? Okay. All right. So if we know that the red numbers are actually exponents with a base of 10, then if we want to do a parallel operation with black 100 times black 100, which is black 10,000, we could do that by adding the exponents, because 10 squared times 10 squared can be found to be 10 to the 4th by adding the two exponents together. So we can add red 2 to red 2 to get red 4, right? And when we divide 1,000 by 100 and get 10, we can actually think of that as dividing 10 cubed divided by 10 squared, which gives us 10 to the 1st, which is like subtracting red 2 minus red 3 minus red 2 equals red 1. So do you see? We have reduced complicated math operations, multiplication and division, to the simple math operations, addition and subtraction, by going to the land of log. So there is magic in the land of log, because we can do complicated math simply. Okay? So let's go back here and see if there's something, right? Examples of magic or superpowers in the exponent world. Okay, so we have witches in the land of log. We have flying monkeys. We have talking animals. We have live scarecrows, live tin men, right? So there's a lot of evidence of magic in the land of log, and of course no magic in the regular world. How do we move between the two worlds? We move from Kansas to the land of log using a tornado. We go back from the land of log to Kansas by tapping our red magic shoes together. Okay? So, oops. So we write magic shoes, magic slippers, I guess they're called, and goes from land of log to Kansas, and tornado goes from Kansas to the land of log. So the way you go from one world to another is not the same. If you want to go in one direction, you use the tornado. If you want to go back the other direction, you use the magic slippers, right? So let's see about how numerically things work in the regular world and the land of log. So we'll look at the regular numbers and we'll look at the exponent or the log numbers. So examples of regular numbers, like we saw, are like 10, 1, 100, 0.01, right? And then we have the equivalent red numbers, which are going to be 1, 0, 2, and -2, for example, right? 0.01 is red -2, and 10 is red 1, right? I would like to write those smaller because they're small munchkin-sized numbers, but then it's going to be hard to see, so I just write them red, okay? So the size, these are regular size numbers, and the red numbers are munchkin small numbers. They're exponent sized, right? Examples of quantities which exist in both worlds, and what are their number names? Okay, so that would be these. I think I got this mixed up. I meant to put the black and just that they're black and white up there, okay? But so up here, black and white, and here they are red, okay? And then this actually goes here. Oopsie. Okay. What quantities exist only in the regular world? So remember, negative numbers don't exist in the land of log. Okay? Examples of math superpowers in the exponent world. For example, multiplication and division. So let's do multiplication. We'll do 10 times 100. And for division, we'll do 100 divided by 10. And so what operation in the land of log is the equivalent? 1 plus 2 equals 3. And 2 minus 1 equals 1. So in the land of in Kansas, 10 times 100 is 1,000. And 100 divided by 10 is 10. So do you see how these red numbers represent how many zeros are in each one of these numbers? If you replace multiplication with addition and you replace division with subtraction, you get the same result. Now, of course, when you're using these black numbers, if you're using multiples of 10, even the multiplication is not significantly hard. But remember, logs work for any numbers. So I could have some weird numbers here that are not 10 and 100, something like 58, and it would still work, okay? How do we change from the black and white number world to the red number world? Well, we use an operation called exponents in one direction, and we use logs in the other direction. So to go from the regular world to the log world, we do an operation called log. And to move back, we do an operation called exponent. Okay? And just to show you what that looks like, I write the transportation methods in blue to differentiate this notation from the black and the red numbers, okay? So I'm gonna write what that looks like. Let's go back here and take a look at this just for a second. So we move from one world to the other with the tornado or the ruby red slippers. Here we're using the log notation to move from the black and white number to the red number. Here we use the exponent to move from the red number back to the black and white number. Okay? And just an easy way to remember how this is arranged, I'm just going to show you something a student taught me a few years ago, which I thought was really clever. If I have log base 10 and we have the red number here and we have the black number here, sometimes it's kind of hard to remember the relationship between this and this. Right? It turns out that this is written on your formula sheet, okay? But there's also, you might not have your formula sheet around all the time. So you could always use something called the Snail Rule. The snail rule works as long as you have the isolated number on the right side and you have the operation on the left side. I can change from this equivalent expression to this equivalent expression by drawing a snail on the left side here. So I'm going to draw a snail, and so as I draw the snail, I'm going to say the conversion. So 10 to the second power is 100. See? 10 to the second power is 100. So I've translated from this expression to this expression by drawing a snail. Now I'm going to go the other way. Log base 10 of 100 is 2. Log base 10 of 100 is 2. See how that works? Cool, huh? Okay. But that's also in your formula sheet. But if you don't have a formula sheet, use Snail Rule. Okay. Now let's talk about this table here, which is going to relate our black and white numbers to their equivalent red numbers. We already know that the red number that corresponds to 1 is 0. And the reason why is because 10 to the 0, or anything to the 0, is 1, right? When we can convert back by putting 10 to the 0 is black and white 1, right? And what would be 10 to the what is 0.1? It would be negative 1. Okay? What about black 10? Black 10 is equivalent to what red number? It would be 1, right? We just count the number of zeros for numbers that are bigger than 1. How many zeros in 100? 2. Okay? Okay, we did all the easy ones. Now we need to look at some weird ones, okay? So what about black, I'm sorry, not black. Red 0.5. I didn't have color printing, so this was black and white, but red 0.5. What is that equivalent to in black and white numbers? And you're like, well, how am I supposed to know that without a calculator? Okay? Actually, an exponent of 0.5 has a special meaning, doesn't it? What is the special meaning of an exponent of a half or exponent of 0.5? It's square root, right? Okay, so what is the square root of 10? The square root of 10 is, I always remember it, that it's very close to pi. Pi is 3.14, right? Square root of 10 is 3.16. Pretty close. And then let's try to find the red number that corresponds to black and white 5 by drawing a graph of the numbers that we know. Okay? So first what we're going to do is we're going to label our y-axis. This will be 1. And this will be negative 1. And here is our x-axis, which goes from 0 to 10. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And I'm just going to graph the points that we have here. For example, 0.1 is the x-axis, negative 1 is the y-axis, because actually this is our red 1 and this is our red negative 1. Okay? All right. So the first point is 0.1 comma negative 1. So 0.1 comma negative 1 would be there, right? Next number is 1 comma 0. That would be right there, 1 comma 0. The next one would be 3.16 comma 0.5. 3.16 comma 0.5 would be about there, right? And 10 comma 1. 10 comma 1. And 100 comma 2 is way off to the right. Okay? Now what I'm going to do is I'm going to draw a smooth curve through these 4 points. And these points I found without a calculator. I found these points just by using math reasoning, right? Of course, I did have the square root of 10 kind of memorized, but... Alright, so this is the shape of the log graph. So you can see that you can reproduce the log graph with a minimum of math knowledge at any time. Alright? Look at how the log graph does not exist on this side of the plane. Because remember, negative numbers in the black and white world do not exist in the log world. So that is why there are no points on this side. What about the point 0 itself? Is there a way to put a red number as the exponent of 10 to get 0? No, because if you put 0, 10 to the 0 is just 1. If you put any negative number, it's just a small number. That is why there's an asymptote here. There's an asymptote on the y-axis. The log graph does not touch the asymptote because for black 0, there is no red number. Black 0 is Uncle Henry. Does not exist. Negative numbers and 0 don't exist in the log world. Okay? All right. All right, so that, let's estimate from our graph the red number that corresponds to black 5. I would say that that's about, 0.7 maybe? I would say 0.7. Okay, that's an estimate. All right, on the final page, what we're going to do is we're just going to rewrite these expressions using the appropriate colors. So, for example, the conversions I always write use blue to write the conversions. So all the conversion notation I just write in blue. All I'm doing is rewriting these expressions using the right colors. And now I'm going to write all the exponent numbers in red. Okay? And then I'm going to write the regular world numbers in black and white. How many zeros is that? 1, 2, 3, 4, 5 zeros. Okay? Red 5 equals red 2, red 2 plus red 3. Okay? So, addition in the exponent world is equal to multiplication in the log world, right? 10 to the 5th equals 10 squared times 10 cubed. We just talked a lot about this in the last chapter, right? When you have a common base multiplied times each other, then you add the exponents. That is why the red numbers get added when we do multiplication in the regular world. Okay? And that's it for the investigation. All right? Hope you had fun.